So section 1.4 is about conditional probability. And so what happens is we say, well, if we know that event B occurred, does that change the probability of event A? So for example, if I look outside and it's cloudy, would that change your probability of it that it's going to rain? Okay, of course it would. So that's what we call conditional probability. So if we know that B happened, does that affect event A? Okay. So we write this as the P parentheses A given B. We say A given B. Your book actually likes to say also A conditional on B. Okay. I'm probably going to stick with A given B. So let's find some of our conditional probabilities. We're going to start by just using some logic to try and find them. And then I'll give you a nice formula. Okay. So you've seen this setup before. It's our cross-classification table or our contingency table. And we want to know what is the probability that a household subscribes to the Atlantic Journal given that they read the Beacon News. So what do you think I can do here? First of all, let's write it in symbols. So what would this look like in symbols, do you think? Which one do I need to write down first, Atlantic Journal or Beacon News? The Atlantic Journal, given that they read the Beacon News. So the part that you already know, that's the part that's given, and that's what comes second when you write it down. So, any thoughts on what numbers I could write down? So if I already know that they read the Beacon News, what's the probability that they read the Atlantic Journal? What do I need to do for this?
Just use the data in the first column.
Because
that first column already assumes they're reading the Beacon News.
So we're narrowing our entire world down to the first column, which is where they read the Beacon News. Okay, so what else do I need to write down then? What numbers do I actually want here? 250 over what? 500,000. The reason being that if we know that they read the Beacon News, there are only 500,000 people total that read the Beacon News, and of those, 250,000 also read the Atlantic Journal. So this gives me 0.5. So if we know they read the Beacon News, then the probability that they also read the Atlantic Journal is 50%. So then I might ask you, well, let's try it the other way. So what is the probability that they read the Beacon News if we already know that they read the Atlantic Journal? So this would be the probability that they read the Beacon News if we already know that they read the Atlantic Journal. So for this situation, let's pick a different color. Okay. What am I going to be focusing on now? The first row, the people that read the Atlantic Journal. So my total number of people that read the Atlantic Journal is 650,000. And how many people of those read the Beacon News? 250 again. So that one I can't do in my head. 0.384. Okay. So if we know that they read the Atlantic Journal, there's a 38% chance that they also read the Beacon News. So that is a conditional probability. We're doing this using logic and what we call a reduced sample space. So basically I narrowed my space down to just the first row, and that was all I cared about. What color is easiest for you guys to read as my normal writing color? Either? Anything but yellow? Okay, I'll avoid the yellow. So let's try our next example. If we roll a 6-sided fair dice, what is the probability of rolling a 6? So this was not conditional yet, just what would our probability be? 1/6. Okay. Just using equally likely outcomes. So let's change it a little bit. Let's say you rolled your 6-sided fair dice and your friend peeks at it and tells you it's an even number. Once you know that it was an even number, now what is your probability that it was a 6? Okay, well let's see. How many even numbers are there on the 6-sided dice? So the even numbers are 2, 4, and 6, so the probability of a 6 is 1/3. Okay. So again, this is just reducing our sample space to knowing that it was an even number. So if you roll the dice and your friend tells you that it is an odd number, what is the probability that you rolled a 6? 0. Because there are no 6s that are odd numbers. So again, we've just done all these problems using our reduced sample space. So now I might give you something that's more complicated, so we're going to learn our formula. Any questions on the reduced sample space? So this is our formula. The conditional probability that A will occur given that B has occurred is the probability of A given B. So what we do is we take the probability of the intersection, so the probability of A intersect B, and divide by the probability of B. Now mathematically, what do we need to assume for this equation? Yes, the probability of B is not 0. In this situation, since all probabilities have to be at least 0, not 0 is just greater than 0, or not equal to, whichever way you want to think about it. Just so we don't divide by 0. So what if, so that's the probability that A will occur if we already know B happened. What if I wanted to do the other conditional probability? So what would you write down if I wanted the probability of B given A? So someone tell me what that formula would be. Okay, so you said it's the same whether I write B intersect A or A intersect B.
Over
Probability of A. Okay, so this is a formula that you need to memorize. Okay? Or I always just think of it as if whatever I know, whatever part is given, I remember that that's the probability that I need to put in the denominator. So the given part or the thing that I know is what I put in my denominator. So we can use this formula now. So let's say that the probability of having clouds and having rain at the same time is 30%. How would we write that in probability symbols? Okay, that is the intersection. So the probability of clouds and rain is 30%, so 0.30. Let's see. What else do they tell us? Now the weatherman says that the probability of it being cloudy today is 70%. That is just the probability of clouds. So if I look out the window and it is cloudy, what is the probability of rain? Okay, so tell me first which order I'm writing this down. Is it C given R or R given C? R given C. Remember, the part that you know is what comes second. We know that it is cloudy. So this is what we're looking for. So we write out our formula, so we know we need the probability of R intersect C over the probability of C. So 0.3 over 0.7 gives me 0.428. So if we look out and it's cloudy, there's a 42% chance that it is going to rain. Now just to emphasize what I said yesterday, what would have happened if you put 0.7 over 0.3? What kind of answer would you have gotten? something bigger than 1, and that should have been a good clue that you did something wrong. So for our next example, suppose 30% of the people in my class do all the homework and get an A. So that means the probability of homework and an A equals 30%. By the way, I just made up these numbers. Don't base your grade off of them. And I also guessed that the probability of a randomly chosen person doing all of the homework is 0.40. So that's just the probability of homework is 0.4. So if you know that you are doing all of your homework, okay, what is the probability that you will get an A? So the thing that we know here is that we are doing our homework, so that's the thing that needs to come second. So what's the probability that you get an A if you know you did your homework? So the formula will be H intersect A over the probability of H, since that's what was given. So 0.3 over 0.4 should give me 0.75. I would guess it's actually a little bit higher. So, questions on this part? Yes. Okay, let's go with you first.
So are H and A and R and C interchangeable? Like, so in the first one, example 23?
Oops. Okay, 23. Okay, this is pretty annoying.
In the known information, you have P, the probability of C intersect R, and then in the equation, you do probability of R intersect C. That's fine.
Yeah. That is fine. So we did learn yesterday C intersect R is the same as R intersect C, and so you'll notice I'm pretty lazy with which way I write them down.
Okay.
Yep. Okay. So we're good? So for our next example, if A and B are mutually exclusive events, find the probability of A intersect B. Sorry, of A given B, not A intersect B. So if they're mutually exclusive events, find the probability of A given B. So remind me, what does mutually exclusive mean? Okay. Yep, so it's impossible for them to happen at the same time, and they don't intersect. So let's start by writing down the conditional probability formula. So if we want A given B, the formula is the probability of A intersect B over the probability of B. Okay. Now, if they are mutually exclusive, what do we know about the probability of the intersection? It has to be 0. So 0 divided by anything is 0. Okay. Why does this make sense logically? So mutually exclusive events says that they can't happen at the same time. So if this is saying, so now if we already know that B happened, what's the probability of A happening? Well, if they can't happen at the same time and we know that B happened, the probability of A happening should be 0. It should be impossible. So let's see if I can make this next part make sense logically. So we want to use Venn diagrams to find the probability of A given B plus the probability of a complement given B. Okay. So let's say that this is our B. And let's say that this is A complement. So A and A complement divide my sample space in 2. And then I have my event B. So if I want to shade A given B, so let's think about this in our reduced sample space format. So if I know that B happened, basically in Venn diagrams, that means everything I shade will be in B. That now my world is narrowed down to just my event B. So if I want to shade A, if I know that B happened, I would be shading here. So basically, we already know we're in B. Now let's shade A. So that's the representation of A given B. Now for A complement given B, again, our world is narrowed down to this B, and we want to shade A complement. So that would be this piece. Okay. So what do you notice about those two pieces if you add them back together? We're going to get the probability of B. And that always holds. So A given B plus the probability of A complement given B will always equal the probability of B. We could do a more mathematical formula, but I wanted you to see the visual here. And for our last example, let's also use a Venn diagram to find the probability of A given B if, what does the next symbol mean? Anyone remember from a math class? Okay, you may not have come across it too much. This is a subset. Okay, basically B is a subset of A means that if you were to draw your Venn diagrams, B is completely enclosed in A. So my sample space, then we have A, and then we have B. So B is completely enclosed in A. And we are looking for the probability of A given B. Now we could write out a formula, so this is A intersect B over the probability of B. So when we look at this, if I wanted to shade A intersect B, what would it look like? Where is A intersect B? A intersect B is just B. So this is the probability of B over still the probability of B, which is going to give me 1. Sorry, ran out of room there. Okay. So that's kind of interesting. Just if we have B entirely contained in A, then the conditional probability is going to be 1. Okay. The reason why is if all of B is inside of A, well, if you know that B happened, then it must be true that A happened as well. Now, these are kind of interesting formulas. We're going about it more just to get you used to looking at the Venn diagrams and just kind of some practice playing with it. These aren't necessarily formulas that you have to memorize. So questions on conditional probability.
So for number 26, would that also be 1?
Here. Not 1, because 1 would still be my entire sample space, but it did add up to the probability of B.
So if we were to make a formula for the addition of the two, I mean, would we not have it be probability of B over probability of B here?
So if we try to make our actual, try to show this mathematically?
That's probability of B given B, is that what that is?
No, this is just the probability of B. Just straight up the original probability of B.
Okay, gotcha.
Okay. Other questions?